Hi there. A couple of weeks ago I decided to buy a 300 watts electronic load, and then I started to search the models offered in the market. Three models caught my attention: the B&K BK8500B and the Siglent SDL1030X and the SDL1030X-E. They all have similar specifications, but the B&K was more expensive and local support could be more complicated if needed. As I am having a good experience with a waveform generator I recently bought from Siglent, I decided for this brand again. The two models from Siglent, these two ones here, have very similar specs, but the X model was almost 30% more expensive than the X-E model. And then I started studying the specifications to find out why. Well, before going deeper into this, let's refresh some basic terms used to specify DC electronic loads. A DC electronic load is basically a resistance which can be smoothly changed electronically using a manual interface with buttons and switches, or remotely with the use of commands. They can normally be programmed for constant voltage, constant current, constant resistance, or constant power. Resolution is the minimum amount you can program for the voltage, current, resistance, or power, and accuracy is the minimum amount the circuit is really able to set. Readback resolution are the final values shown on the screen for the voltage, current, resistance, and power, and readback accuracy are the real values set by the circuitry. Okay, now going back to the Siglent models X and X-E, there are small differences when we compare the specifications. Now, considering the specifications for the two Siglent models, we see here that there is a difference for the accuracy in the constant current mode, another difference here in the resolution and accuracy in the readback voltage, and a third one here for the resolution in the readback current. It's 0.1 milliamp for the X model and 1 milliamp for the X-E model. But notice that the accuracy is the same for both models. So I don't think this item is that important. I have made here two simulations so we can see how important are the differences. In this one I considered a current of 3 amps in the constant current mode using the 5 amps range, and if you use the formulas we will find that for the X model the accuracy is plus minus 6.5 milliamp or 0.2%, and for the X-E model the accuracy is 10.5 milliamp or 0.35%. And in this other simulation we calculated the accuracy for the readback voltage for 12 volts using the 36 volts range, and we can see here that the accuracy in the X model is 12.5 millivolts or 0.1%, and 13.7 millivolts for the X-E model. This is 0.11%, so it's basically the same. So I came to the conclusion that I would not pay 30% more for such small differences, and then I decided for the SDL1030X-E. I have prepared 3 experiments to test my electronic load, or dynamic load if you wish. And in this first one I measured the ripple produced by this 30 volts 3 amp linear power supply. The specification says it should be less than 2 millivolts peak to peak. Well, the first thing to do is to check the intrinsic noise of the oscilloscope, which is 500 microvolts or 0.5 millivolts peak to peak, and be sure that this low pass filter is on. This is a 20 megahertz low pass filter and should be on for this type of measurement. Then I will set the load to constant current, check if the current range is 5 amps and the voltage range is 36 volts, and then I will turn the power supply on. Notice that for this measurement it's important to use a BNC to banana adapter, and you can't use the ground strap in the probe. It will pick up extra noise. Well, you can see here that the noise has increased to 1.3 millivolts peak to peak, even with the output of the power supply disconnected. And now I will connect the output and switch the load on. Now we have here around 2.6 millivolts peak to peak, and subtracting the 0.5 millivolts peak to peak of the oscilloscope, we will have around 2 millivolts peak to peak, which is consistent with the manufacturer specification. In this second experiment I will do the same measurement, but now for this Manson SPA8230G, 13.8 volts, 23 amps, with a current of 21 amps to avoid exceeding the maximum power of 300 watts of the load. The ripple specified is 50 millivolts peak to peak or less. In this case, the BNC to banana adapter won't fit. Then I prepared this other one to do the measurement. So the intrinsic noise is the same, about 500 microvolts. The input filter is on, and then I will turn the power supply on. Massive increase in noise, and then I will set the load to, let me check first the range. The current range is 30 amps, voltage range is 36 volts, and current 21 amps, a little bit more. And switch the load on. We have here around 47 millivolts peak to peak, so less than the 50 millivolts peak to peak specified by the manufacturer. In this experiment, I am gonna use the battery test function of the electron load. I have here this small and portable frequency counter I built. It's a 5-volt device, and I would like to use this cheap power bank. It cost me about $350 to power the counter. The first thing we have to do is to see how much current it drains. You can see there that, well, let's consider about 100 milliamps. Here we can see the specs for this 5-volt power bank. The capacity is 2000 milliamp hour or 7.4 watt hour, and it can supply up to 1 amp. 2000 milliamp hour is the same of 100 milliamp for 20 hours, and 7.4 watt hour is the same of 370 milliwatt for 20 hours. If you use this value here in this equation, power equals voltage multiplied by current, we'll have for the current 74 milliamp for 20 hours, which is different from this other specification here. And the reason is that we considered here a constant voltage of 5 volts, which is not true. The voltage will drop along this 20 hours. Well, the frequency counter is meant to be powered by an USB interface, 2.0 or 3.0, whatever. In the case of the USB 2.0, 500 milliamp is the maximum current that can be supplied, and the voltage should stay between 4.75 volts and 5.25 volts. Well, we will program the load with these two values here, 72,000 seconds, which is 20 hours, and 4.70 volts, which is a little bit less than the minimum voltage accepted in the specification of the USB interface. So let's program the load. As you can see here, it's connected, and shift aux battery. Current. (100 milliamps). Constant current. V range 36 volts, E range 5 amps. V stop. V stop it's already here, 4.7 volts, and the T stop will be 72,000 seconds. That means we have here two conditions: minimum voltage and time. Anyone can disconnect the load from the power bank. So let's start discharging the power bank. As you can see, the test is finished. Battery test complete. And the voltage dropped to 2 volts after 8 hours and 32 seconds.